Testing. Down low. And better video. There you go. Looks good. I don't want to back off. All right, we've got 2 items of business to take care of today. One's review for the next exam on your chapters 6 and 7 in Brown on atomic structure and periodicity. And the other is we need to complete a lab exercise. Okay, so let's here. I got a few picked out. This is your review document. In fact, this is the key for the review document. See how much we really know about number 1. When ignited, that must be fun. Uranium burns, compounds burn with a green flame. The wavelength of light given off by this flame is greater than that of. So let's think of how. Let's see, what do we have to choose from? Red, radio, infrared, ultraviolet, yellow. So if we have the wavelength here, we got the longer wavelength on this end, which would be radio. And we've got, what's the shortest one? Ultraviolet, I think. So we've got UV here. Then we have visible in the middle. Oh, we've got infrared. Okay. So radio, we've got infrared here. And then the visible range is going to have red, there's a yellow here, red, orange, yellow, green, blue, indigo, and violet. Violet's not there, so we don't have to worry about it. Okay, so wavelength. The wavelength of light given off by this flame, green, is greater than that of what? Well, it's greater than blue and it's greater than UV. Blue's not in there, so it's greater than UV. Okay. Let's see, how about number 3? Oh, just barely made it. I'm going to start writing this up. Which of the following frequencies corresponds to light with the longest wavelength? So if we look at the relationship of wavelength to frequency, as wavelength gets bigger, frequency has to get smaller. So the longest wavelength would be the smallest frequency, the smallest number for frequency. So it would be the smallest number for frequency. 13.5, there it is, B. Yeah, there's B. You got kicked off the top. Okay. How about 7? Yeah, I still see that. Picking it up. Yep. 7. What's the wavelength of a photon of red light? 7. The wavelength of a photon of red light, whose frequency is 4.55 times 10 to the 14th hertz. Okay, so we're back to that formula again. we need to know this part. So we take this one is equal to frequency divided by the speed of light. So we want this value divided by 2.9979 times 10 to the 8. Here it is. Okay. So the frequency is 4.55 to the 14th. And then C is 2.9979 10 to the 8th. We have to be sure that our units are correct. All right. Frequency, this is actually, the frequency is in the reciprocal seconds. And then this one is meters per second. See that right? We're looking for wavelength. I got it backwards, don't I? If this one is here, this one goes underneath. There we go. So I need to invert these before I divide. There we go. So I get 6.59 times 10 to the minus 7 meters. So how many nanometers is that? Well, after you do this for so many years, all you have to do is move this to the right 2 places. 659 nanometers. We could do a unit conversion, right? Say nanometers to meters, cancel the meters, leave us with nanometers. But you get the same answer. All right. I have my hands. All right. Number 9. Let's try number 9. Which of the following types of radiation has the shortest wavelength, the greatest energy, and the highest frequency? Those are all correlated together. Shortest wavelength means the highest frequency. Right. This one gets small, this one gets big. How about the greatest energy? Does that correlate? High frequency means high energy. Right? Based upon Planck's equation. Number 9. Right. E equals Planck's constant times frequency. So if we get high frequency, we get high energy. Okay? So which one's the highest energy? Or which one has the shortest wavelength? You could pick any one of these. They're all correlated together. So all you have to do is just find the one that matches whichever one you choose. Shortest wavelength would be ultraviolet radiation. Highest energy, ultraviolet radiation. Highest frequency, ultraviolet radiation. They all correlate. How about 10? What's the energy of a photon of blue light? Not too good here. Blue light is 453 nanometers. We want to know the energy, so we're back to that same equation. Planck's constant times frequency. Or what can we substitute in here? We can say frequency equals C divided by lambda. So we could say here H times C divided by lambda. Okay? But we have to have the right units of measure. Right? That wavelength here is in nanometers. We need meters. 4.53 times 10 to the minus 7 meters. Right. Now we can plug those values in. Plug this one in here. This one's the speed of light. And Planck's constant is in useful information. So let's look it up. Let's see. There it is. Okay. Kind of feet of light. Yeah, I'm going to go up and more. Just for a second. Divided by the wavelength. There we go. And the units of measure, meters cancel, seconds cancel, units will be joules. And that should be 4.39 times 10 to the minus 19 joules. Let's see if that's reasonable. Let's see, this is 8. This would be a positive 7, would be 15. 15 from 34 is about 19. 19. Yeah, minus 19. Okay. This thing's up. 10, 11. We have to scroll that one. How many of the following is or are correct? Okay, we have to take them one at a time. The importance of the equation E equals mc squared is that energy has mass. Yeah, I think that's a fair statement. They're interconvertible. So I is true. Electromagnetic radiation can be thought of as a stream of particles called photons. That's true too. Let's see, 3. Electromagnetic radiation exhibits wave properties. That's true too. Energy can only occur in discrete units called quanta. Yep. That relates to this one. Particles of photons. These two are tied together. That just means light can be treated as a particle and a wave. 12, 13, 14. Let's see, the following list of observations, choose the one that most clearly supports the conclusion in the following 4 questions. Okay. Okay. So electrons have wave properties. I think these statements are supported by this fact. Electrons have wave properties. Electrons have wave properties. The emission spectrum of hydrogen, no, that's Bohr's model of the atom, where the electron moves from one level to the other. Doesn't have a wave property. In fact, Bohr's model assumes that the electron is a particle. The photoelectric effect. Photoelectric effect says that light is a particle, not an electron. Scattering of alpha particles by metal foil. They were talking about Rutherford's experiment there. No, that's not it. Okay. Diffraction. Haha. Diffraction is characteristic of anything with wave properties. Remember what diffraction is? There are several ways to demonstrate it. When a wave strikes a barrier and there's an opening in it, that opening serves as a point source for a new wave. That's diffraction. If light, in this case, electrons. If electrons are only particles, then they would come in here like this, and they would end up over here like that. But we also know that electrons, if we pass them through a small enough slit, they will do that. You'll be able to detect out here. So electrons also have wave properties, and they exhibit this characteristic, diffraction. The cathode ray is a stream of electrons. That's part of particulate behavior. And we use this diffraction property of electrons in a rather expensive piece of equipment called an electron microscope. And because the electrons have a much shorter wavelength than light, we can see smaller structures using electrons than we can using light. Okay, 13, electromagnetic radiation has wave characteristics. Right. Well, that's diffraction again. Anytime you're talking about waves, if you see diffraction, home in on that one. Let's see, 12, 13, 14. Electrons in atoms have quantized energy. Right? Yeah, quantized energy. This is a good one here, emission spectrum of hydrogen. If the energy is quantized, then only certain wavelengths can be emitted. And that's where you get the line spectrum of hydrogen. And that's based upon the restricted movement of the electron in that space outside the atom. It can only move to certain positions. And when it does, it either absorbs light or emits light. So under what circumstances would it absorb light? Which direction would the electron move? It would move away from that nucleus, right? Because it's promoted to a higher energy level if it absorbs light. And if it drops from a higher energy to a lower energy level, it will emit light. So you can see the emission spectrum of hydrogen would be like wavelength, and you would see these four lines at definite wavelengths. But if you shine white light through atomic hydrogen gas, right, and you'd have to be sure that the conditions were right, then you'd see bright light here and dark lines here. It would have not an emission spectrum, it would have an absorption spectrum. In fact, that's how helium was discovered in the atmosphere of the sun. Before it was discovered on this planet, it was discovered in the sun. That's why it's called helium. That's from the Greek for sun, from its absorption spectrum. So light from behind the atmosphere of the sun was shining through, and it was producing dark line spectrum. And that's how they identified it. It wasn't characterized by any other element on the periodic table. So they knew they had found a new element. Okay, let's see. 14. Let's see, we want to tackle this. And spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. Now, this is a true statement. We just have to correlate it with one of those four Roman numerals before. So what is the de Broglie wavelength? The de Broglie wavelength is similar to this expression. Except that talks about light, and de Broglie wavelength can be applied to any form of matter. It just has a different velocity. So if it's moving at a certain speed, then you can correlate it with these values. We didn't go into that in much detail, so it's not that critical. But an accelerated electron will, and that's how the electron microscope works. The electrons are accelerated to high velocities, and they produce these wavelengths that are much, much shorter than light wavelengths. Okay, so which one does it correlate with? Well, like I said before, if it has anything to do with wavelength, it has to be diffraction. Okay. Let's see. 17. Oops, I skipped. There we go. 17. For which of the following transitions does the light emitted have the longest wavelength? Okay. If you want the longest wavelength, that means the smallest frequency, which means the smallest energy based upon Planck's equation. So we're looking for the smallest energy. So when we transition from, the electron transitions from a high principal quantum number to a lower principal quantum number, it will emit light. Okay, so the longest wavelength or the lowest energy will be the transition where the energy levels are the closest together. Okay, so remember that model where we had energy, let's see, distance from the nucleus corresponded with energy. So if we have n equals 1 here, n equals 2 is way up here, and n equals 3 is a little bit closer, and n equals 4 is even closer to that. Okay, so the transition that gives the most energy or the shortest wavelength would be like from 4 to 1. 2 to 1 would be pretty substantial too. It would be higher energy. We want the smallest energy. So we want to transition between these higher levels. So 4 to 3 would be the smallest transition. 4 to 2 would be bigger. 4 to 1 would be bigger than that. 3 to 2 would be even bigger than these. All right, so 4 to 3 would produce the smallest energy, longest wavelength. That would be the red end right there. All right, that was 17. How about 18? When a hydrogen electron makes a transition from 3 to 1, which of the following statements is true? Well, let's see. If we go from 3 to 1, we're dropping from a high energy to a lower energy, which means emission, correct? We're going to emit energy. Energy is emitted. That's true. Can't be emitted and absorbed at the same time, so 2 is out. The electron loses energy. Is that true? Yeah, it has to lose energy in order to emit it. Electron gains, no, it can't do that. Can't do these two together. Electron cannot make this transition. Okay, I think we're searching around for something to fill in empty space. So we've got 2 of them, the 1 and 3. Let's see. 19. Let me scroll down. Okay. When an electron in a 2p orbital of a particular atom makes a transition to the 2s orbital, a photon with this wavelength is emitted. So it just tells you what it is. The energy difference between these two is what? That's simply 19. That's simply this one, or like the transition we did before, H times C divided by wavelength. Okay. So we just convert this to meters, 6.291 times 10 to the minus 7 meters. And that's your speed of light. This is your Planck's constant. That gives you your energy. Should be this one right here. 1920. Okay, we can still see 20. In Bohr's atomic theory, when an electron moves from one energy level to another energy level, more distant from the nucleus, what happens? Well, it's going from a lower to a higher, so it has to absorb energy, right? So energy is absorbed. I don't know why I put that one in. It was kind of redundant. We've already covered one that talked about that. 23. Which of the following best describes an orbital? What is an orbital in our atomic theory? It's a place where we think the electron lives, right? But is it exact location? No. It's a volume of space where we predict that the electron is most likely to occur, to be found. Right? Heisenberg's principle says if we know the energy or the velocity of an object, we can't know where it is, not when it's that small. So which one fits that goal? Let's see. Unlikely to be found now. No, you can't find all of them there. That's not what that means. Orbital. Space in an atom where an electron is most likely to be found. Okay. We got it. It's C. How about, oops, skipped a page. Back up. 25. Yeah. Now we're going to look at atomic structure in terms of their quantum numbers and letters, the letter equivalents. So let's just review. What are the 4 quantum numbers? Principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. Okay? So N can be what? Start at 1 and go up in units. The L can be any one of these, and we start from minus N through 0 to plus N. Right? How about M sub L? Well, we take, excuse me. Nobody said anything. We start with 0 to N minus 1. There we go. And this one, we take L minus L, 0 plus L in whole number increments. And then this one can either be 1/2 or -1/2. Okay, so now that we've reviewed that, how many F orbitals have the value n equals 3? So we're going from 3. How many F orbitals? Can we have F? Well, remember the L's would go in this sequence. This would be S, P, D, F, and G if you need it. Actually, we don't need it. If 3 then, so what could possibly be 3? It could be 0, 1, or 2, right? There are no F's in that at that level. All right, so that's why the answer is 0. No F orbitals can have n equals 3. It's impossible. It's 25, 26. While we're here, this is ridiculous. This one. 26. How many F orbitals have n equals 6? Okay. Now we're talking. If we go up to n equals 6, there we go. Now what can we have here? We can have 0, 1, 2, 3, 4, and 5. Right? We could have all of these possibilities. So how many F orbitals have n equals 6? Well, we have to look at this one. Now that we have that one, we have F equals 3. Then we say how many, these are actually the orbitals. So we have -3, -2, -1, 0, +1, +2, +3. Yeah, I'm picking that one up. So that's 1, 2, 3, 4, 5, 6, 7. So that's how many orbitals we can have under 6. Because F can have this many m sub L's, 7. And that's characteristic of all F's. That's why you can have 14 elements with the F orbitals filling, because 2 electrons each, 2 times 7 is 14. That's why the lanthanides and the actinides have 14 places here. Okay, 26, how about 32? Yeah, almost. Okay. I need to keep this up here. How many electrons in an atom can have quantum numbers n equals 3, L equals 2? Okay. I'll keep that up there. This is 32. Okay, how many electrons in an atom can have the quantum numbers n equals 3, L equals 2? So if n equals 3 and L equals 2, okay, then we take 2 and spread it out. And it can have -2 up through +2. So that's 5 orbitals. With these quantum numbers, 5 orbitals and 2 electrons each is 10. So you can have 10 electrons with these quantum numbers. Because you can have either this one or that one or that one or that one or that one, and then either one of those. Okay, 32, 33. Okay, how many electrons can be described by the quantum numbers n equals 3, L equals 3, m sub L equals 1. So n equals 3. And then we're going to go back over here to 3. But now we're restricting it to m sub L equals 1. Okay. Is that possible? No, wait a minute. That's not possible. 0, 1, 2 is all this one can have. Right? So that won't work. 0 electrons will have these quantum numbers. All right? And I'm getting kind of messy here, so I'm going to have to erase this. That was 33. Okay, I'm going to skip down to 40. This one, we ought to knock this one out pretty quick. I just wanted to put this one in there to emphasize the history of the development of the periodic table. Who was the first chemist to recognize patterns in chemical properties of the elements? Remember that one? Your first inclination is to say Mendeleev because he's given credit for the periodic table. Or even Julius Lothar-Meyer, who put his periodic table together about the same time as Mendeleev. They were preceded by this guy right here, Dobereiner. He recognized the relationship among triplets of elements, called them triads. So he was the first one to recognize patterns in the chemical properties of elements, Dobereiner. Okay. 44. Let's see. Yeah, there we go. The complete electron configuration of 10. Okay. Put on our thinking caps here. 10. We need to know what? How many electrons it has, correct? So how do we get that? Atomic number. Right? Atomic number. If it's a neutral atom, the number of electrons is going to be equal to the number of protons. So 10 is right here, 50. This is going to be fun. 50 electrons. Okay, where do we start? 1s2, 2s2, 2p6. Then we'll go down to 3. 3s2, 3p6, 3p6, then 4s2. Then we go back to 3s. 3d. 10. How many we got so far? That's 2, 4, 10. 2, 4, 10. That's 20, 30. So we got 30 done. We need 20 more electrons. So 3D gets us to here. Now we're back to 4P, gets us 6 more. Okay? So that's 14. Now what do? We swing around to 5s. 5s, 2. Right? So now we're down to 12. And now we're down to 4D. We can use all those 10, at least 2. So now we're back to 5P, right? 5P, 2. Here we go. So let's see, 5P2. Oops, that's not the right order though, is it? 4S, 3D, 4P, 5S. Wait a minute. What's the difference between this one, that one?
Top one has 5D.
Ah, thank you. This is the right. Yeah. You can either write it out like that, or you can do process of elimination. You know that 10 is in the 5th row. So this is going to be 5P2, 1, 2. So you know that Possible, throw that one out. And then you go in and look at the structure, go backwards, right? If you go backwards, 5, then you have to go back to 4 for the D's. So that means you can't do this one, you can't do that one. So you can eliminate it that way. All right, that was 44. Let's see. 46. This checks to see if you remember the rules. The statement that the lowest energy configuration of an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle is a particular set of degenerate orbitals. We didn't talk about this, what degenerate means. Degenerate means their orbitals are at the same energy level. That's all that means. I don't know why they call it that. That's what it means. So which of these rules applies to that principle? Here's the key. Maximum number of unpaired electrons. When you say unpaired electrons, in this context, you're talking about Hund's rule. Remember when we were filling up orbitals? Like if you have a p orbital, then you can put them in like that, like that, like that. Then you can go back and start pairing them up. Lowest energy possible is unpaired first, then you can pair. So this is B, Hund's rule, is best associated with that statement. 647. Oops. Now let's see if we understand how the periodic table is structured in general terms. What did I say, 47? Oh, I'm jumping. Yeah, okay, there we go. So the electronic configuration of this element is krypton as our core. Then we have 5s2, 4d10, and 5p2. Right? So I would look at the 5p. Where are you going to find 5p? Well, there's 5. And you go all the way over here. These are the p's. 5p. Wait a minute. We just drew that one. That's 10. So what does that make? What's the best answer for this one? Is it metal or non-metal? That's a metal because of where it's located here in the chart. It's to the left of that zigzag line. Okay. It's not a transition. It's a lot of lanthanide, actinide. If it were lanthanide or actinide, we'd have an F here filling up. If it were a non-metal, we could have a P filling up for non-metal, but it would have to be relative to that zigzag line that shows us metals and non-metals. And it's most likely to be a metal when it has this few p orbital electrons. Because in order to get back to krypton, it would have to lose 4 electrons and still have this in its orbitals. 47, I think I got 48 more. So, yeah, 48. So an element with electron configuration of xenon 6s2, 4f14, 5d7. Okay, so we've gone through 6 here. We've gone through the F's here, and then we're back to D, 5D, 7. So we're going 2, 3, 4, 5, 6, 7. That should be iridium, which makes it what? A transition element. Okay. 48, 52. I hope we'll get into some exceptions. We'll be back at that now. Right. Where we left off with the lecture last time was with basically everybody behaving themselves, filling left to right the way we would expect them. But there are some places in the periodic table where the lowest energy level for electrons is going to be different than what you expect. And I hope we hit a couple of those in this discussion. How about iron has so many electrons that are unpaired in its d orbitals. Okay, so let's look at iron. What is iron going to be? All right, if we're going to just talk about the d orbitals of iron, we can use our abbreviated version. 52. So if we follow iron backwards, we eventually get to argon at 18. And they don't do it, but I like to write the number in there also. Keep track of my electrons. All right, so after argon, we get to 4s2, and then 3d what? 1, 2, 3, 4, 5, 6. 3d6. Okay. Now, how many sublevels of this one are there? Well, the D's can have 5, right? P's can have 3, D's can have 5s because they can go -2, -1, 0, +1, +2. Right, so we can have 5 sublevels here. 4, 5 for this D. 6, we got 1, 2, 3, 4, 5, unruled 6. So we have 4 unpaired electrons in iron here. We missed one of the exception spots by 1 element. Actually, 2 elements. Chromium is an exception. I'll come back to it if I have to. Let's see, that was iron 53. Here we go. Oh, 53 is going to reference that configuration above. So let me scroll back there a bit. Here we go. Consider the following electron arrangements for the next 2 questions. So there we go. So this structures, these structures, and this, of course, they left out the 1s electrons in this. They're only talking about the principal quantum number 2, which represents the ground state of nitrogen. So if we're only talking about 2, 1s is already filled, of course. And then what have we got left? Well, if we take nitrogen is 7, let's see, where are we? 53. If nitrogen is 7, and we've already used up 2, then we got 5 more to go. Right? 2s and 2p. So 5 more, that means 2 here. So we got 3 electrons left. So we're going to have 3 there. So how do they go in? 1, 2, 3, 1, 2, 3, just like that. So we got to fill up the 2s, right? Then let's B and C out. And then we've got to put unpaired electrons. Here we go. It has to be A. That's the only possible way it could be. Okay, how about the do 54? Yeah, 54 also. So which represents the ground state of N- ion? So if we have, I'll just leave that up there. If we have N- 54, what have we done? Just add another electron, right? So if we had 7 before, now we have 8 electrons. So we have 1 more electron. Where does it go? Right there. So we've got, and that's just for this one. Both of these S's are full. Right? So 2s has to be full. There, there, there. And then we have to have a paired and 2 unpaired. Paired and 2, no, that's not right. They have to both be up. That's a trick. Here. Up, up. Which was what? C. No, E. Excuse me. E is the correct answer for 54. About 58. Scroll that one. There we go. Of the following elements, which has occupied d orbitals in its ground state neutral atoms? Occupied d orbitals. That means they're coming from transition elements, right? So all I have to do is look down here and say, all right, which one's transition? Nope, alkaline earth. Nope, alkaline earth. Silicon? Nope. It's a metalloid, actually. It's non-metal. Phosphorus? Nope. It's a representative element. Below it, it's in a nitrogen. Chlorine? Oh, wait a minute. Which one has occupied d? Okay. Back up. I was thinking in terms of which one is filling d orbitals. That would be transition. Which one has occupied d orbitals in its ground state? Let's look where we're coming from, right? If we move across here, barium, yeah, barium has d orbitals filling because it went through 5 and then back down to 6. So it has 4d orbitals filling barium. Actually, it has fill 4d for barium. Calcium, no. Calcium hasn't got to its d's yet. Calcium comes from here, there are no d's there. So calcium's not one. Silicon, no, silicon hasn't got there either. Phosphorus, no. Chlorine, no. Barium is the only one that filled d orbitals. That's got any electrons in the d orbitals. All right, 58. Skip a few. A lot of redundancy here. 67. Oh, okay. Good deal. 67. So which of the following processes represents ionization energy of bromine? Remember what the requirements were for measuring the ionization energy of an element. Bromine has to what? Start as a gas. And ionization means it's going to lose an electron. And then what's left over? Bromine plus, and it's a gas also. Okay, so we have to have bromine gas. Nope, nope, could be. Nope, nope, can't be. It's not diatomic. It has to be, it has to be the atom. So C is the only possibility. Can we just check it out? Okay, Br plus gas, yeah, plus one. That's it. C has to be it. $67. 68. Okay, order the elements. Sulfur, chlorine, and fluorine How? Increasing ionization energy. Okay. Ionization energy. Let's see. Do we have an abbreviation for that? I don't think we did. First ionization energy, we could say, increasing ionization energy. So we look at them on the periodic table. Where are they located? So there's sulfur, there's chlorine to the right, and then fluorine above. So we go sulfur, chlorine, fluorine. Should be the correct order. Yep, sulfur, chlorine, fluorine. Increasing ionization energies, lower left, upper right. 69, I think. Yep. 69. I will have to scroll this one. Okay. Order the elements, those same three elements in terms of increasing atomic radius. So what's the trend with atomic radius? Which direction do they increase in size? Upper right, lower left. Right? They increase in size going down because we're adding electrons to higher energy levels. They increase going to the left because we're reducing from right to left, we're reducing the effective nuclear charge, fewer protons, which allows the electrons to move further out. So it'll be just the opposite as before. Fluorine, chlorine. Yeah, fluorine, chlorine, sulfur. Here should be D. Okay, and 70. Which one of these has the highest ionization energy? And I assume that since they're all elemental, which one has the highest ionization energy, first ionization energy? Right. So we have sodium. Let's kind of order them. Sodium, magnesium. Oh, they're all in the same period. So sodium, magnesium, aluminum, silicon, and phosphorus, right? And sulfur. Phosphorus, sulfur. Yeah. Left to right. That's left to right, top to bottom here. Choose the element with the highest ionization energy. The trend is left to right increasing, right? Because we increase the number of protons. So the highest ionization energy should be sulfur. Uh-oh. No, it's not. That's one of those switchbacks. Okay. So let's look at their structure. Phosphorus and silicon, phosphorus and sulfur. Phosphorus will have 3p3. 3p3. Sulfur will have 3p4. Okay, it's becoming clear now. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. This one will have the lowest energy, lower energy than phosphorus because of that one paired electron that is experiencing repulsion by its neighbor. It takes less energy to get that one off there. I think the one we looked at last week was nitrogen, oxygen. So if I went with my first impulse, I would have got the wrong answer. Phosphorus is actually lower in ionization energy. Sulfur is actually lower than phosphorus because of that. That's why I put it up there. And I caught myself. 82. There it is. Select a correct set of quantum numbers for the highest energy electron in the ground state of 10. Okay. 10. So we only need to know the ground state of 10. So if we look at 10 and go backwards, we've got krypton 36. And then we work our way from there. So we got 5s, 5s2, 4d10, and 5p2. Okay, so what would be the highest energy electron in here? Well, if we write it correctly, the highest energy electrons are right there. Right. So what would be the quantum numbers for this? Well, N would be 5, L would be 1, correct? And then we have M sub L's, which could be -1, 0, +1. So we've got 2 electrons in there. So let's see which ones can we satisfy with 5 and 1. Right. A, C, and D. Right. Those are the only 3 that would work. Okay. So let's look at this one. 5, 1, 2. Is 2 possible? No. M sub L cannot be 2. All right, let's go to the next one. 5, 1, and 1. 5, 1, and 1. Yeah, that's possible. But how about the M sub S? Right, it has to be +1/2 or -1/2. Right. So that can't be. So that's 5, 1, 0. Yeah, that's possible. And +1/2. That's it. D has to be it. That's the only one that is legitimate. '82, '85. Which of the following equations correctly represents the process involved in the electron affinity of X? Right? Electron affinity. So we got what? We got our X, has to be a gas. And electron affinity means we're going to add an electron to it. And what does that give us? That gives X minus gas. Okay, so that's the one we're looking for. Got X gas, there's one possibility, there's another possibility. Nope, that kicks an electron off. This is the one that absorbs an electron. There, C. Gas, gas, and there's your electron. So it has to be C. '85, let's see. Pretty soon I'm going to hit one that's going to dump me again. How about '89? Let's see. I better scroll a little bit. There we go. So to answer '89, we need to use this information. These are the energy values for those quantum numbers. And notice the smaller the quantum number, the more negative the value. So we're getting closer to the nucleus. That means a lower energy level, which means more negative. Okay, back to in the hydrogen spectrum, what's the wavelength of light associated with N equals 3 to N equals 1 electron transition? So we're going from 89. We're going from N3 to N1. Okay? You don't have to pull out that big equation, right? With a 1 over N squared minus 1 over N squared. You don't have to do that one. Because you're given the values of the energy right here. So what you have to understand is the energy that's emitted is the difference between this energy level and that energy level. Right? So this is the final energy level. N equals 1. So it's going to be the change in energy is going to be the energy for 1 minus the energy for 3. Right? Final minus initial. So the final is here. Minus 2.178 times 10 to the minus 18 joules. And then we subtract 3 minus 0.2420 times 10 to the minus 18. There. Okay. So that makes this a plus. These are both have the same powers of 10. So we just need to deal with the coefficients. That makes that a plus. 0.2420. And this is a negative 2.178. Okay. So this is going to be 0, 6, line them up, 3, and that's 9, this is 1. So it's a negative 1.936 times 10 to the minus 18. Right? If I did that right. Let's add it back up. 8, 7, 11. Yeah. So I take this value of joules and put it in the, we want the wavelength of light. Okay. So we take this value of joules and use this equation. Planck's equation, H, like that. So this energy value goes here, Planck's constant goes there, gives us a frequency. Or we can do this. There we go. That would be easier. Then we can plug in, we know this value, that's a constant, solve for this one. And then you end up with this value right here, 1.03 times 10 to the minus 7 meters. You just have to be sure you plug in the right values here. This is the key. Find that value, goes here. That's a constant, solve for the lambda. That's going to come out as meters. Right? And as luck would have it, meters is the answer. So nanometers, that would be 103 nanometers. That's pretty short wavelength. Definitely in the ultraviolet. Actually, might even be lower than that. Ultraviolet, let me think. Vacuum ultraviolet goes down to about 150. So that would be pushing into the X-ray, maybe soft X-ray. All right, 89. Let's see, 94. We're going to have to use, consider the following. Oh, no, we don't need that stuff up there. Let me scroll. Consider the following representation of the 2p orbital. Okay. Okay, I'll go for that. Looks like sort of like a dumbbell without the bar in between. Which of the following statements best describes the movement of electrons in a p orbital? Can we describe the movement of electrons? No, that's impossible. Right? If we're saying this is where they're located, then we can't say anything about how they move. Velocity, momentum, whatever direction, none of that's possible if we're saying this is where they are. So the best one for that one is electron movement cannot be exactly determined. That's true. That's the valid answer for this one. Okay. 95. And I'm going to scroll that one too. How many electrons can be contained in all the orbitals with n equals 4? Okay. So let's do some n equals 4. So what possibilities do we have for L? 0, 1, 2, 3, correct? Okay. M's of L. All right. Now, underneath this one, we can have these, and then each one of these, that one can have 1, this one can have 3, this one can have 5, and this one can have 7. S, P, D, F. F can have 7, D can have 5, P can have 3, and S can have 1. So below that, what's left? Spin. So we have 7, 10, 16. 16 times 2 for the spin, which is 32. So at that n level, we can have 32 electrons. Okay? So let's see, 4 would be 4. 1, 2, 3, 4, 5, 6. Oh, wait a minute, that's 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 8. Did I count that right? I counted it wrong. Let's count it by 2s, because that's how many electrons. Okay, 4, fourth level. 2, 4, that's 3. 2, 4, 6, 8, 10, 12, 14, 16. This is 4. 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. Why is that not adding up? 2, 4, 6, 8, 10, 12, 14, 16. 16 and 20 is 36. Let's see if I did this right. At n equals 4, okay, we can have a 0, 1, 2, 3. That's correct. Then each one of these, this one can have only 1 level. This one can have 3 levels. This one can have 5 levels. This one can have 7 levels. That's right. Oh, this is F. So this one can have 2. This one's 6, which is 8. That one's 10. That one's 14. That's 32. So that's right. I must be counting wrong. That means 32 elements can be covered at that level. Because each time you add a proton, you add an electron. .95. Let's see how we get on time. So we want to split at 3 o'clock. Okay. 95. 96. Small but important, the energy differences between 3s, 3p, and 3d. Three S, 3p, 3d. So they're generally the same energy level, but there are differences. And that's why they're filled in order, this one, then that. And actually there's a 4s in here that's stuck in there. But the differences here are such that how do we determine the differences here? Well, remember with the S's, the 1s has no nodes in it. It's just an energy distribution like this, and this is probability. So the 3s is going to be like, it'll have 2 nodes in it. Like that. 3p is only going to have 1 node, but it's going to be in here like this. And the D, the 3D, is going to have no nodes. It's going to start in here like this. So the discrepancies, the differences, the slight differences in energy are due to penetration. This one penetrates deeper. This one penetrates the next deep. This one penetrates not at all. Oh, okay. So the answer would be the penetration effect. And then 4S would have to fit. It would be out here somewhere, but its penetration would be down less than D. This one. It would penetrate down here. That's what puts 4S below 3D. And that's demonstrated by the way the periodic table is structured. 4S is here, then 3D, and then back to 4Ps. They're in order of energy. Let me see if I can do this one. Yeah, 101. So we've got this element, whatever it happens to be, and it's got a configuration with 5S, 4D, 5P2. Well, that's 10 again, isn't it? We've done that twice already. Yeah, 5S too. So 5S would be here, and then 4D, and then 5P2. Okay. The formula for the fluoride of this one would be what? How many fluorines would you have there? The key to this one is valence electrons. How many valence electrons are in that element? They have the same principal quantum number. There are 2 there and 2 there, which means you have the possibility, if you only lose these 2, which is possible, then you would have an E with a +2 charge. If you lose all 4 of them, you would have an E with a +4 charge. So that means this could either be 2 or 4. And then you look at your choices, right? It's not 14, it's not 1, 6, or 8. So EF4 is the best answer out of that bunch. Okay, and that's true about 10. 10 occurs in 2 ions, in a +2 and a +4. We used to call it, +2 used to be called stannous when it's in a compound. So when you look on your toothpaste tube, stannous fluoride would be the 10 2+ ion. 101, 103. There we go. Which of the following have 10 electrons in the d orbital? Okay, this is a tricky one too. You look at the, if you need 10 electrons in the d orbital, that means the d orbital is full. Right? So the obvious one, manganese is in the middle of the Ds. It doesn't work. Iron's in the middle of the Ds. It doesn't work. Copper and zinc are on the right-hand side. Zinc is far to the right. It has definitely 4d10. No, 3d10, excuse me. But if you go back to copper, we would normally say that copper is 4s2, 3d9. And this would be 4s2 also. The way the energy levels work is the lower energy level, the d orbitals, which are 5 of them here, they would tend to be, for this one, of course, it's obvious. Right? So there are 10 electrons there for this one. But for this one, we're saying that it only has 9 there. It's counterintuitive that you would want to put another electron in here, but complete orbitals are lower energy than incomplete orbitals. When you get this close to a complete D, the energy level is such that you would steal one of those, take one of those 4s's and put it there. That's one of the anomalies, right? When you get to copper and zinc. The same thing happens when you get to 1, 2, 3, 4, chromium and manganese. They're half filled. Right? So we would have 4s2, 3d5 would be manganese. But chromium would be 4s1, 3d5. Because even half-filled d orbitals are more stable than if you try to pair up an electron there. Okay? If you try to do an unfilled, unhalf-filled. So that's where the discrepancies lie in the electronic structure of elements. It's when you get to those possibilities for half and complete orbital filling. Okay, so I didn't write the number up there, but the answer is 2 of the above. Copper and zinc both have 3d10s. I just explained why, that's all. Same thing happens in the f orbitals down here in the lanthanides and actinides. 1, 2, 3, 4, 5, 6, 7. So gadolinium would be 4f5, 4f7. And europium would also be 4f7, but it would steal an electron from the 6s, I think. Let me see. It's got them there, doesn't it? No, it steals it from. Okay, that's even weirder than. We're not going to deal with that. that's way too weird. We'll only do that if we have to. All right. And let's see, what else do I have left? Okay, this is potentially a brain twister. So rather than lead you down the wrong path, I'm going to look at how I solved this before. Number 108. We have time to do that one. Okay. All right, 108. Okay, suppose we have a planet that's a lot hotter than the Earth, maybe like Venus. And hydrogen ground state is actually where that electron is in N = 4. So it's really hot. And there's enough energy there to keep that electron in N = 4. what's the ratio of ionization energy for hydrogen in the planet compared to that of Earth? So we know the ionization energy of Earth is going to be larger than it is for this planet, because the electron has further to go from n equals 1 to infinity rather than n equals 4 to infinity. Did anybody try this one? No, I don't blame you. So if we look at that, that equation, hold on a second. If we use, if we use this equation, by the way, if this is the energy of an electron at any place, any position, based on Niels Bohr's model, right? If we look at that equation, then where the change in energy that's required for ionization is the energy at infinity minus the energy at whatever n is. Okay? So that means we'd have to do this one minus that one. So we'd stick a 1 in here for Earth and a 4 in there for this planet. But for this one, what would it be? Right? If we put infinity in here, right? If we say at infinity, what's n equal to? Well, n's infinity. So anything divided by infinity is what? 0, right? Mathematically speaking. So that term drops out of that one. And all you have to do is say, all right, the energy of ionization is just you plug in the number here and you ignore the infinity part. Right? So if we put 1 in there for Earth, what's the ratio? They're looking for what's the ratio of ionization energy. So for delta E, ionization energy of hydrogen on the planet compared to Earth. Okay, so the planet is the exoplanet, let's say, and then the delta E for Earth. That's the ratio that we want. Then if we ratio these two, then those terms would be canceled out, right? So really what we've got is a ratio of 1 over the exoplanet, which is 4 to the 6 to the 4 squared, excuse me, 4 squared. And this one is 1 over 4 to the first power. So it'd be, is that right? Oh, no, excuse me. 1 squared. 16. So 16 here is in the denominator, correct? Delusion. We're ratioing energies of XO to Earth in terms of ionization energy. So what I've already done is cancel these terms out because they're the same on top and bottom. So now we're ratioing this one, which is 4 squared, which is 16, 1/16 to 1 over 1. So that ratio is actually, if we flip it over, 1/16 is the ratio, 1 to 16. So that's why the answer is C. You could probably logically figure it's either 1/16 or 16 to 1. And it depends on the terminology here, which one are we ratioing? The ionization energy on the planet compared to Earth. So the planet is here, Earth is here. If it said the ratio of Earth to the planet, it'd be the other way around, and then it'd be 16 to 1. Those are the kind of questions they put on standardized tests, like the American Chemical Society would throw at you if you're planning on taking a standardized test. I don't know. Do you have to take one?
I have to pick the T's next.
Oh, the T's. Okay, you'll be fine with that. I mean, if potential nurses can pass it, you can pass
I have to get past the NCLEX eventually. That's
it. The which one?
NCLEX, NCLEX, it's to become a registered nurse.
Oh, okay. That must be tougher.
Yeah, it's going to be after the nursing program. So I'm sure.
Okay. And then, is that like passing your boards?
Kind of, yeah.
Yeah, okay. Let's see. I thought I had one more. That was 108. Yeah, 116. See if I can do 116, then we can go in the lab and have some fun. Okay. The first three levels of the hydrogen atom are shown below with their energies in joules. Okay, so there we go. Which answer contains all the possible photons that could be generated by transition among the three levels and no others? Just the transitions among these levels. Which photons that could be generated? Okay, we're saying that can be emitted. So we've got the electron has to move from a higher energy to a lower energy. Lower to higher, we'll get it because that would absorb. We want to generate those electrons. So we've got to go from high to low. So actually, this is a math problem. I mean, like a probability problem. So you got transitions. Let's see, what is it called in math terms? Combination versus permutation. I never could get those straight. Which one is with repeated sampling? I think it's permutation. You can throw them back in, it's a resample. But combination, once you pull one out, you can't put it back. Anyway, so we got what possible transitions? Well, we can go from here to here. Right? We can go from here to here. Or we can go from here to here. Right? That's it. And that would emit light. Okay? So this one can't be it. That one can't be it because there's only two of them. That one can't be it. There's only two of them. 1, 2, 3. So logically, in a multiple choice test, we use test taking technique and say it has to be D.
Or E, computers.
Does not compute. Oh yeah, okay. That's why I put that in there. So you'd have to go do it. All right, so the photons would have what energy? Well, in that case, you would just say, let's see, final minus initial, final minus initial, and final minus initial. Those three. So it's really not a big calculation. You just have to subtract the final from the initial in 3 cases and see if they match. And what I would do is, let's see. Well, if they've got the same exponents, I'd leave them alone and subtract. If they've got different exponents, I'd change one. Maybe change this one to the, well, no, because you got choices here. I change this one to minus 18. Change that one to minus 18. So that would make this one 0.5 and that would make this 0.2. Right? Okay. I think I've fumbled it out around enough.
Yep. So we'll have an exam on this material next week.
And get into the next. Actually, I think we just got two more exams to do.